Here we'll look at the assembly code to write our instructions. This assembly code is also called as the register transfer language, or the RTL, and very commonly used to specify the assembly instructions. The three important fields here are the opcode. This specifies what the instruction is supposed to perform. Source, which are indication of the input operand specifiers, and destination, which specifies what are the output operand. So the input operand or the source are the registers from which you're going to read the value, and destination is the output operand to which you're going to write the values. Opcode obviously specifies what the instruction is supposed to do. So here is a simple example of opcode, which is dadd. The destination is R1. The two source operands are R2 and R3. And if you want to translate this simple opcode, it would be R2 is added to R3 and the value is stored in R1. The dadd is the opcode. Most often the opcode is intuitive. That is, if you read the opcode, you should be able to tell what it is implementing. So in this particular case, if you read dadd, you can say there is add, which kind of indicates that this is going to do some kind of addition. And that's traditionally the way opcodes are designed, so that they can identify what the instruction is doing. The destination is always fixed. It is always closest to the opcode. So in this case, R1 is a destination, so you're going to write to that value. R2 and R3 are the source operands from which you're going to read the value. Now the MIPS assembly language arithmetic statement can have, similarly you can write it for dadd, and you can also do dsubtract, in which case you would say R1, R2, R3. Here R2 minus R3 and the value is put in R2. So the value of R3 is subtracted from R2 and put in R1. The position of the destination operand is always fixed. It's always closest to the opcode. Each arithmetic statement generally performs only one operation. This makes it easy to write the opcode. So the opcode is not some complex opcode which can do multiple operations. It will do exactly one operation. Each arithmetic statement will fit in 32 bits and specifies exactly 3 operands. By fixing the number of bits in an instruction, we can make the decode aspect of the problem easier. If you look at x86, which is what Intel uses, the size of the instruction can vary between 2 bytes to around 8 bytes. This generally makes it difficult to decode it because you need to read the initial bit sequence to understand how many bytes you want to decode. Whereas in MIPS, we simplify that. We don't have this flexible number of bits. We just have 32 bits as an instruction. We decode the 32 bits and we execute the instruction. Instructions are simpler, which makes it easy to decode them. Now in this particular case, we can specify this with exactly 3 operands. There are other instructions where the number of operands might vary, but in this format there are 3 operands. Now those operands are all contained in the data path register file. So we have a register file which is going to have R1, R2 and R3. Now in certain cases we might also put some immediate instructions where the immediate value will also be in the data path. But in this case there are 3 registers. And most often the operand order is fixed, which indicates that the destination is always the first register. So the key points here to remember is each arithmetic instruction performs exactly one operation. Size of the instruction is 32 bits and there are 3 operands specified. Instructions are like registers and words of data, and all of this are 32 bits long. The format we use here, we call this as the R format, and the R stands for register format because we only have register specifiers in the opcode. So here's an example for the dadd R1, R2, R3 and how this particular instruction is laid out in the instruction memory. So the first thing we will look at is the destination. Here the destination register is RD. So R1, which is the destination specifier, is actually going to have the bits specified by RD. R2 and R3 on the other hand are source specifiers, as we mentioned, and those two will be specified by RS1 and RS2. Now we will use 5 bits to identify the register file address. The 5 bits will tell us that we can have at most 2 to the power 5 or 32 register file. So the 5 bits are the address specifiers. So for example, if you specify an address as 00000, 5 zeros, then it would be the register number 0. Similarly, if you specify 00011, then it would be register number 3, and so on. So we can specify the exact registers from which we can read the values and write the value. The opcode is generally specified by a combination of the opcode bits, which is the top 6 bits, and the function bits. The opcode, given that you have 6 bits, you can have a maximum of 2 power 6 or 64 different opcodes. Certain instructions, particularly here, dadd, is defined by a combination of opcode as well as the function bits. Now, when you do an addition, let's say you have 2 operands A and B, you will do A plus B. When you do something like subtraction, particularly in the system, you will do A minus B, which is nothing but A plus B complement plus 1, which is in 2's complement, which is the standard way of doing subtraction. So subtraction by default is also an addition. Only thing is you negate B and then you add 1 to it. Therefore, the opcode for both addition and subtraction are identical. But the function bits will specify how to negate B and how to have this carry to come in to your ALU. And that's why we will have the similar opcode bits, but we'll have a different function bits. This will allow us to scale and have larger number of opcodes. And the last thing we have here is a function, a shift amount, which is 5 bits to shift particularly for shift instructions, right? Shift left, shift right, and so on. So this is the most common format for a R format. So you have the opcode bits, you have the register specifiers, and then you have a shift and function bits. The next thing we'll see is the MIPS storage. The MIPS general storage holds 32 64-bit registers. So we have 32 different registers. Each register is 64 bits wide. The number of bits that we require to specify any register file address is 5 bits, right? For example, here if you see, you have source 1, source 2 address. All of them are 5 bits. 5 bits will allow us to decode and figure out one of the locations. Now, when you figure out one of the locations, you activate the cells and you read it out. So you get 64 bits as the two source data 1, source data 2. So these are the two data that you can read, both of which is 64 bits. Now once you do some computation on this data, you would write the value to the register file whose address is specified by the destination address. Again, the address is 5 bits to identify which register number you want to write to, and then you have the 64 bits write data using which we can write the data to the register file. So we have 32 different locations. Each location is 64-bit wide. We also have a write control signal which is enabled when we want to write a value to the register file. This could be true because in certain cases we may not write every time to a register file, and we may have explicit write control signal to enable when we would write to the register file. Traditionally, registers are faster than main memory because this is based mostly on SRAM cells, which is faster to access. But if you have several register files, they can tend to be slower because we have to decode them. So for example, we have 5 bits. These 5 bits have to be decoded so that we can access the register and we can read them. If you are going to have, say, 128 register file or 256 register file or say 1024 registers, then you will have decoders, and this decoder logic becomes significantly larger and they will consume a lot of time to figure out which registers you want to access. And the number of read-write ports also impact the speed. So if you have more write ports or more read ports, they will also slow down your register file. Traditionally, we have between 80 to 120 register file. We have separate ones for integer registers and floating point registers. And we can create similarly 32 64-bit register file for the floating point. So the most important thing here to remember is we have a register file. Register files are faster than main memory. The size of the register file is traditionally 32 locations in MIPS that we're going to study, each of 64-bit size, and we have both for integers as well as a floating point.